welcome everyone. This is the circuit theory class. And as part of this class, this is circuit theory basically forms the foundation of electrical engineering, right. In electrical engineering, you have all kinds of sub branches. So, you could have microelectronics, VLSI. So, double E microelectronics, VLSI, communications, power systems, control engineering, machines, right. So, all of these are sub areas of electrical engineering, and circuit theory forms the foundation of all of this. So, today everything that you see around you, everything, the cameras, this computer, the screen, mobile phone, everything has a deep hand in electrical engineering, right. Everything is done by electrical engineers. If the EE engineers go on strike, all of these are going to fail immediately. So, it is going to be a complete disaster, fine. So, EE is underlying all of the technologies that you see today, and therefore, you taking this course, you being part of the EE program, you have done the right thing. You must tell yourself you have done a good job, you have done the right thing, because EE can take you and give you careers in all of these different avenues and more. So, what I have not mentioned over here, computers, banking, finance, these are all careers in EE. Okay. So, of course, banking finance does not come under circuit theory, but they can easily be launched from EE. And not just that, even in physics, astronomy, all of those careers can be launched as a EE student. So, EE is actually a fantastic place to be, especially in 2025. Fine. Okay, great. And this course, circuit theory, forms the foundation of EE. So, we are at the right place at the right time. Okay, great. Now, the plan for this course is as follows. Today, we will be talking about electrical circuit quantities and just foundational talk. Today's lecture is going to be a foundation of the foundation, and then starting from the next class, we are going to dive deeper and deeper and deeper. Today's class, you will find that a lot of the concepts you already have heard of or probably even know from class 12, from whatever you have studied for JEE, I do not know, H.C. Verma, what have you studied? H.C. Verma, and then you have studied, what else have you studied? Resnick and Halliday in class 12, physics. What was your favorite book? Which one? Oh, come on. University Physics was written by Barnard, no, Sierz-Zimanski. Yes. Sierz-Zimanski, yeah. So, Sierz-Zimanski, University Physics, or even Resnick and Halliday. My favorites were Resnick and Halliday, and then I used to study this H.C. Verma in those days. I do not know, He is still around, right? That book is still around. Yeah, these books are still around. Okay. So, these are the books which you have studied, and in today's lecture you will find that there are going to be elements. There are always going to be elements of what you have studied in those books. However, there is going to be much more. We are going to do much more than that, and we are going to do it in depth. Okay. To start with, so I will just give you a brief course outline, and our first thing today is going to be electrical circuit elements and electrical quantities. That is what we will talk about today. And then next class onwards, we are going to start the other modules, and initially we will start off with a discussion on graph theory. Graph theory is not drawing graphs on graph paper. Okay, it is something totally different. It is a branch of mathematics which we are going to talk about, right, and how from graphs we can make circuits and what are the properties of circuits that come out of graph theory. And you will find what we are going to discover in this course, in this discussion, is that a lot of the basic circuit analysis techniques as well as several theorems can simply be discovered from graph theory. Okay. So, we are going to spend some time on graph theory, and then we are going to move on to theorems. So, when we talk about theorems, our basic theorems are superposition, Thevenin, Norton, reciprocity, actually we will do reciprocity theorem before that. So, we will do Telegon's theorem, reciprocity theorem right over here, and here we will do superposition, Thevenin, Norton, maximum power transfer, and a few more theorems like substitution theorem and so on. Right, that is the plan. And then after our discussion on theorems, circuit theorems, we are going to also do basic circuit analysis, mesh method and node method. So, two important circuit analysis techniques are going to be covered. Yes. All right. So, after this we will move on to first and second order circuits, which you might have seen a little bit of in your class 12. Right, and this is going to be followed by Laplace transforms. You are going to parallelly learn Laplace transforms, or maybe we will be able to teach Laplace transforms before you have studied Laplace transforms in the maths course. So, we will be running a little ahead of the maths course. This is going to be followed by phasors and sinusoidal steady state. So, this is kind of the broad plan, all right. Just by the way, as electrical engineering students, for any, your plan is to become an engineer, you need to buy a calculator, Have you bought a calculator already? Yes. Okay. So, for this course you will need a calculator and you will need a good one. The calculator you will need should be able to operate on complex numbers. So, you are going to need complex addition, okay, complex subtraction, complex multiplication, complex division and argument magnitude. You are aware of these operations? Yes, good. Because in EE we use complex numbers all the time. Towards by the time this course ends, complex numbers will be running in your blood. Okay. In your maths course, how do you describe a complex number? A plus I times B is a complex number. The EE people, they do not like this, okay, because I in EE refers to a current, okay, it does not refer to the imaginary I. So, I small I we refer to small I as current in a circuit and therefore, EE people have used the letter J for square root of minus 1. Okay. So, we exclusively use, so we even have our own symbol for square root of minus 1 overriding the maths guys. Alright. We use complex numbers heavily in engineering. In electrical engineering, complex numbers are used heavily, very heavy usage of complex numbers. Your calculator should be able to operate on complex numbers. So, if you still have not purchased your calculator, make sure that the model you buy has all of these features, right. Magnitude, phase as well as multiplication division of complex numbers. Fine. All right, great. So, with this we are going to start this course. We have more or less discussed the books. So, number 1, there is a book by Van Valkenburg. No. There is a second book by two gentlemen, Hyatt and Kamerly. Okay. And there is a third one. So, the first book is quite heavy on the theory, it is complete, it does a very good job with the theory. The second one, Hyatt and Kamerly, has a lot of practice problems. So, if you want to practice before the exam, okay, not just before the exam, if you want to practice to learn, use this book. It has a lot of worked out examples and lot of exercises. Okay. And traditionally these two books have been used by EE students over the last 50 years, if not more. Okay, they are very popular books. There are multiple copies available in the library, right, and in bookstores all over the country. So, these two I would strongly recommend. A third book which was written by me, it is freely available from the AICTE website. Okay. And it follows the AICTE syllabus, because they had asked me to write this for their particular course content, and that course content is more or less what we are going to teach over here in this course. There are going to be a few additions and a few subtractions. All right. So, this you will be able to access from the AICTE website, and it is called Electrical Circuit Analysis and Network Theory. All right. So, it is freely downloadable. I think you might have to register on their website before you can download. They like to know who is downloading what book, and I think it has translations available in Hindi and couple of other languages as well. So, in case you would like to access the Hindi version, even that is available on their website. However, that said, the number of worked out examples and the number of exercises in the third one is far lesser than what is available in Hyatt and Kemmerly and in Van Valkenburg. So, beware of that, but nevertheless it is a complete book which deals with, which has all the theory in one place, all the material in one place. Okay. Any questions so far? You have a question? No. So, shall we start? Okay. So, the first thing on our agenda today is to discuss electrical quantities and the circuit elements that we have. So, whenever we start with quantities, what are our basic quantities in electrical engineering? Voltage, it is measured using units volt. So, that is the unit VOLT, and if I want to abbreviate it, I write it as capital V. Okay. Whenever it is the name of a person and you abbreviate, we are going to write it as capital V. Fine. Current unit is ampere and the abbreviation is capital A. Very good. And then what else do we have other than voltage and current? Resistance. Okay, resistance, unit ohm, symbol capital omega. Fine. And then what else? Opposite of resistance is conductance. 1 by resistance is conductance and the unit is Siemens. Capital S, not G. Okay. The symbol is G. Just like R is used for resistance, here the symbol is G, the unit is Siemens. So, capital S. More units, more quantities, what else? capacitance. Okay. Farads, capital F, because it is being named after who is the scientist? Faraday, Michael Faraday. Okay. And then lastly, not lastly, we have many more. Inductance, Henry, capital H. Notice that when I am writing the unit in full form, I am writing it in small case, all lower case, and the reason why is, why am I writing it in lower case? The abbreviation is capital letters, but the full form is not capital, it is all small. Why? Yeah. So, if I start with a capital letter, then I am actually talking about the scientist, I am not talking about the unit. Okay. So, if I talk about capital AMPERE, then I am talking about a person named Ampere, right. But when I say 1 ampere with small letters, then I am referring to 1 unit of current. Fine, good. Then other quantities, watts, sorry, power is given in watts, capital W, and energy joules, capital J. Anything else that comes to your mind? Magnetic field, flux density, unit? No, Tesla, capital T. Anything else? There are many more units. There is Webers, that is flux. Then what else? All right. One of my interesting units along with all of these is dB. Have you heard of dB? Where have you heard of dB? What is dB? Decibels. But look at the funny case. The first letter is small d, the second letter is capital B. Why? The unit is actually Bell. Who is Bell? Alexander Graham Bell. Thank you so much for recalling his name. We are actually talking about Alexander Graham Bell, who invented the telephone. Okay, that is the capital B, and deci is like your decimeter. That is why it is small d, it is not something major. So, decibels, and what is this a unit of? It is the unit of a ratio, right. It is either 10 log to the base 10 of a ratio, or it could be 20 log 10 of a ratio. All right, let us modify this. When is it 10 log and when is it 20 log? So, it is 10 log when it is a ratio of 2 powers. Or energies, okay. Whereas, it is 20 log when it is a ratio of amplitudes. Amplitudes means amplitude of voltage, amplitude of current, amplitude of electric field. Okay. V squared by R is the power. Power is V squared by R. or I squared times R. Power is V squared by R, it is also I squared times R, correct. So, if you want to work on the ratio of two powers, P 1 is V 1 squared by R, I 1 squared times R, and P 2 is V 2 squared by R, I 2 squared times R, right, and then you take 10 log of this, then what do you get for the voltage ratio or the current ratio? You get 20 log. Okay. So, whenever we talk about these amplitudes, right, quantities which are going to be squared to get you a power, right, those quantities we take decibels by doing 20 log of the ratio, whereas if we are actually talking about powers, we do only 10 log. So, it depends on what kind of ratio it is. If it is a ratio of powers, it is 10 log, otherwise it is 20 log. Okay. And then the naming convention, deci is small d, Bell, Graham Bell, capital B. Fine. All right. So, these are all the units. Okay. These are all the electrical quantities. Any other electrical quantities that come to mind? Coulomb, charge, unit is Coulomb, given as capital C is the unit. Okay, good. Now, along with these units, we also have scaling factors. So, in engineering, so my point, my lament has always been that our schools teach you lakhs and crores. The Indian number system is very confusing. Okay. In engineering, our number system goes in steps of 10 power 3. Okay. So, 1 then 10 power 3 is called kilo. Abbreviation is small k. 10 power 6 mega, 10 power 9 giga, 10 power 12 tera, okay, and so on and so forth, exa. It keeps going on in steps of 10 power 3. All right, you could go downwards also. 10 power minus 3 is milli, 10 power minus 6 micro, 10 power minus 9 nano, 10 power minus 12 pico, 10 power minus 15 femto, and then you could keep going on and on and on, atto and so on. Fine. So, this is our number system. So, when we talk about pico amperes, small p capital A is pico amperes, 10 power minus 12 amperes, right, and we only work with range of 10 power 3. Okay. So, our calculations also become much easier to deal with. You do not have to do in JEE, unfortunately you are used to 10 power 8, 6.2 into 10 power 8, no. Okay, we do not do 6.2 into 10 power 8, we will do 620 into 10 power 6, 620 mega, all right, or you could do 0.62 giga, but not 6.2 into 10 power 8, we do not write it that way. Fine. So, the engineers they always write it either as mega or as giga or as whatever it is, milli, micro, right, no random 10 powers involved. Okay. In physics and chemistry, you have been doing all of this 6 point, how much is the charge of an electron? 1.6 into 10 power minus 19 coulomb. Okay. So, such a bad number. Okay. You should write it as 0.16 into 10 power minus 18, or you could do 160 into 10 power minus 21. Okay. Do not do it, this minus 19 is no good. All right. Why? Because if all your numbers are like that in steps of 10 power 3, then when you multiply them, you will still get a step of 10 power 3. So, milli times kilo cancel out. Okay. Milli times micro will give you nano, and so on. So, these interoperate, right. That is why we stick to these, right, and we do not write those exponents at all. Okay, good. Next, we are going to discuss the different circuit elements that we are going to deal with in this course. And our first most favorite circuit element is the resistor. Yeah. So, you love the resistor, right, R, the current, if it is I and the voltage V, then what is Ohm's law? V is equal to I times R. Okay. This is something you have learnt a long time back, and by now this is in your bloodstream. Okay. Now, can you think a little bit in terms of energy? Where is what is happening in the resistor? Electrical energy, electrical power is being converted into heat. It is being dissipated as heat. Fine. Is this okay? The voltage times the current is always going to be the power across any circuit element. The voltage times the current is the power, and therefore, in this case the power is either V squared by R, or it could be I squared times R. Fine. All right. What EE students always do is draw circuit elements, draw their circuits in a way such that the plus is at the top, the minus is at the bottom, and current travels from top to bottom. They will try very hard to do it this way. Okay. This is just good practice. The way I have drawn it, the current is coming from the top, flowing to the bottom, okay, and the potential difference is indicated with plus on the top, minus at the bottom. This is general good practice. Why do we do this? Because we think of potentials like water. Water flows from higher level to lower level, very good. So, just like that, current also is going to hopefully flow from higher potential to lower potential. So, you basically think of voltages like the water system in your house. There is a pump, right, there is a pump outside the house, there is a pump. The pump puts the water up into the tank on top of the house, and then when you open the tap, the water flows from the tank downwards. Okay. So, the pump takes the water from low potential to high potential. So, the pump works like a voltage source, like a battery. Okay. It takes the water from low potential to high potential, and now when you release the water, the potential energy in the water is released and it becomes kinetic energy, and it flows through the tap. Okay. So, this is the analogy that we always have in mind. EE students always have this water system analogy going on. somewhere on the back side of your brain, right, you are probably thinking of water, and we want you to think of water. All right. This analogy is always to be kept in the back. Okay. That is also why we put the plus on the top, minus at the bottom, and we indicate current flowing from top to bottom. All right. Okay. So, this is your favorite component, and in electrical circuits typically you will have a voltage source, right. What is a voltage source? So, our symbol for a voltage source is not the symbol you are used to. We like to draw it this way with a circle and a plus and minus inside, and we do not do that battery thing. Okay. So, this is a voltage source, and the voltage source is basically in the business of converting one form of energy into electrical energy. Okay. So, it could be a battery is converting chemical energy into electrical energy. It could be a turbine, a wind turbine, or a hydroelectric turbine, or a thermal plant turbine, which is converting mechanical energy into, or kinetic energy into electrical energy. It could be what else? A solar cell, which is converting light into electrical energy. It could be, what else could it be? Nuclear power, it is going to convert kinetic energy into electrical energy. Yeah, hydro kinetic energy, water kinetic energy is converted into, all that is covered in the turbine. It could be an antenna. Okay. What is in an antenna? Have you heard, do you know what an antenna is? Have you seen an antenna? Dish antenna, you have seen, there are antennas inside your cell phone. Okay. So, the antenna is converting electromagnetic energy into electrical energy. All right. So, all these possibilities are there, and possibly even more, right. Thermal energy, you could have a thermistor, right. You could convert heat directly into electrical energy, all kinds of possibilities are there, and all of these are going to be sources of power. Okay. So, in electrical engineering, in circuit theory, we are going to represent them in the form of a voltage source or in the form of a current source. Okay. Note the arrow here is pointing up. Why? Because this is the pump. Okay. I have the pump in my mind when I am drawing the source. All right. So, that is why I am pointing it up. So, these are all sources of power, and then what is happening in the resistor? All that power is going to be wasted as heat. Not just that, hang on, we could also convert the power into mechanical energy in a fan. I would like to represent that also, sometimes is modeled as a resistor and something else maybe. I would like to convert the power into sound, right. What would that model be? How would I model that? As a resistor, maybe some other component involved, but mostly as a resistor. I would like to convert it into light, LED, right, your audio system, sound, right. So, the resistor is a model. So, the R over there is not necessarily an object which converts it only into heat. It can be any kind of a load, we call it a load, right. It could be any kind of a load. It could be a machine which is running, it could be a fan, it could be a light, it could be an audio music system, right. Anywhere where energy is being converted from electrical energy to something else, right. All those places you could model that circuit element as a resistor. You will have to model at least a part of that circuit element as a resistor, where the conversion is happening. Is this okay? Am I clear? So, a resistor is not just converting it into heat, it is being modeled as that. The R on the screen over here is a mathematical object, where the mathematics describing the object is Ohm's law. Are we clear on this? Any object which follows this is going to be represented as R. Agreed? Okay, great. We have consensus. We have agreed on describing any object that follows V equal to I R as a circuit element called R. Okay. All right. The other two, what are the other circuit elements that are very interesting? By the way, this voltage source, what is the mathematical description of the voltage source? So, I can describe it graphically as follows. Is this okay? Some constant. Is this the correct graph for the voltage source? V is a constant for any arbitrary current I. Yes, any current I, V is constant. So, this is the mathematical description of this circuit element, voltage source circuit element. All right. Unfortunately, this is mathematical only. You cannot possibly have a circuit element in real life which behaves like this. Why? Not just internal resistance. Let us think of the power. This is a mathematical object. Power I with, if such an object exists, your name is Adib. Adib has given me the right answer. If such an object indeed exists, entity, such an entity indeed exists, then it can give me infinite power. I can take I forever, right. I can be infinity, V is still a constant. So, the power it is delivering is going to be V times I, which is infinity. So, it can generate infinite amount of power, and I know that this is not going to happen. Why? Because the voltage source, if it is a turbine, then it will only be able to give me as much power as there in the water that is spinning the turbine. Okay. If it is a photodiode, if it is a solar cell, then it can give me only as much power as there in the light that is falling on the solar cell. It can't possibly give me more, right. It can't give me infinity. Fine. So, this description that we have on the screen is mathematical. We are going to use this, but I am letting you know that this is mathematical only. There is no such object. I have just proved that it can't be the case, right. Such an object, such an entity cannot possibly exist. Fine. How will you describe this current source? just the reverse, right. The current is a constant for any arbitrary voltage, and here also this circuit element is mathematical. Such a thing cannot possibly exist, because otherwise it is going to be generating, capable of generating infinite power. Fine. So, even though these do not exist, we are going to use them in circuit theory. All right. So, advance warning is being given. All right. What other circuit components are we going to use? Any other favorite circuit component? A capacitor and an inductor. Okay. And here once again I am going to make I come from top to bottom, and the voltage is indicated from top to bottom. Fine. And what is the description? What is the mathematical description of the capacitor? We want to relate I and V. I do not want Q. Let us stay away from charge. I is equal to C dV by dt. All right. And in this case it is V is equal to L di by dt. All right. Rate of change of current times inductance is the voltage, rate of change of voltage times the capacitance is the current. All right. You could also write it as an integral equation, but we are not going to do that. All right. You could also write it in your free time, you could write it as voltage is equal to integral I by C dt, okay, for the capacitor, and for the inductor you could write current is equal to integral I by L V by L dt. Okay. However, in EE you are not going to do that even in your free time, do not do it, write it this way only. Why? Because we do not like integration, especially we do not like indefinite integrals. Why do not we like indefinite integrals? There is some arbitrary constant involved, and we do not like these arbitrary constants. We are going to stick to this as the mathematical description, no integrals. Fine. Any questions? Good. I have one more component to discuss, and that is called a mutual inductance. And the mutual inductance is basically two coils, two inductors which have a shared core. What is the core? So, you have an iron core and you have this is coil number 1, and you have another coil over here wound on it. This is coil number 2. Okay. So, two coils which share a common iron core, and when this happens, the flux generated by the current in coil number 1 also goes through coil number 2, and therefore, when the current in coil number 1 changes, the flux generated by coil number 1 changes and that induces a voltage in coil number 2 because of Dash's law, Faraday's law. Okay. Changing magnetic flux is going to create an EMF, a voltage. All right. So, because of that a voltage is going to be created in across coil number 2. Similarly, a current in coil number 2 is going to create a flux that is going to go through coil number 1, and therefore, whenever I have a changing current in coil number 2, the changing current in coil number 2 is going to create a changing flux through coil number 1. The changing flux in coil number 1 will induce a voltage across coil number 1 because of Faraday's law. Fine, this is why this happens. And this circuit element, this pair of coils is a very popular circuit element, and we call it a mutual inductance. Fine. So, let us call the current in coil number 1 I 1, the voltage across coil number 1 is V 1, and then the current and voltage across coil number 2 are V 2 and I 2. Fine. Now, this is a coil and it has an inductance. Both of these are coils. So, they have inductance. Let us call this inductance L 1 and let us call the other inductance L 2. Okay. So, this is our starting point, and then we already know that V 1 is going to be L 1 times d I 1 by dt, even when the second coil is not there. Suppose the second coil is not there in the picture, right. Throw the second coil out, even then V 1 is going to be L 1 times d I 1 by dt. And if the first coil is not there, then V 2 is going to be L 2 times d I 2 by dt, if the first coil has not been involved. Fine. Now, we throw in the two coils together. When I have the two coils together, I am going to have a mutual coupling between them, and the result is going to be that V 1 is going to be L 1 d I 1 by dt plus an additional term, which is going to be proportional to d I 2 by dt, and this we call it as M. All right. And exactly the same term comes for the second mathematical description. V 2 is going to be M times d I 1 by dt plus L 2 times d I 2 by dt. Okay. So, this is the description of mutual inductance. EE students also put two dots over there to indicate the orientation of the coupling, right. If both are clockwise, coiled clockwise, or if one is coiled clockwise and the other is coiled anti-clockwise, then the effects are going to be opposite. The orientation of the flux through the second coil, is it the same as that of the first or is it the opposite, right. That is indicated by the dots on the top, right. And if I have dots on the top, both of them, then this is basically the setup. Fine. Any questions so far? You should have one question at least. I always had a question, are these two M's guaranteed to be equal to each other? And the answer is yes. These two M's are guaranteed to be equal to each other all the time. Why? it is outside the purview of this course. Why? So, I will not answer this, but I will be happy to point you to Griffiths. No, electromagnetics, electrodynamics by Griffiths. There is a book, nice fat book, right. Go to the chapter where they discuss mutual inductance, and he has nicely proved that this m, this term, this proportionality constant is going to be equal no matter what in both cases. Okay. So, proof of this exists over there, please look it up if you want to. Otherwise, you go with me and believe that yes, it is going to be equal. All right. Now, these circuit elements that we have discussed, some of these R, L, C and M, do they generate power? Yes? No? It generates power? It converts power. Is there a, does it produce electrical energy? No. These circuit elements are called passive circuit elements. And my test for passivity is, does it produce electrical power or not? Does it generate electrical power or not? Does it convert some other energy into electrical energy or not? Fine, that is my test for passivity. But the other two, which are the other two? Voltage and current sources. Those two convert some other form of energy into electrical energy, and therefore, they are not passive. What is the opposite of passive? Active. Fine. And to this list you can add more. Suppose you bring up some other component from your memory, diode. You remember the diode? Where would you place it? Passive or active? Passive. Fine. Solar cell, active. Agreed? Photodiode, active. Even though it is a diode, it is a photodiode, it is an active component. All right. There is one component which you will not be able to give me the right answer, that is the transistor. Okay. The transistor is a 3 terminal device. We place it in the active bucket, even though you would want to put it in the passive bucket, right. We place it in the active bucket. Basically, the reason being that it converts between the different ports. It takes in power through one port, one pair of terminals, and throws it onto another pair of terminals. Okay. So, it transfers power from here and gives it over there. So, that is the reason, that is basically the reason why we put it into the active bucket. All right. Otherwise, the natural test is, does it generate power, does it convert other forms of energy into electrical energy or not, and that gives you the answer whether it is passive or active. Fine. All right. Next, we are going to discuss linearity. And linearity does not refer to the straight line, kind of related, but it is not exactly related. think of your circuit elements, all right. And what we are going to think of over here is a 2 terminal circuit element. It could be anything, right. This 2 terminal circuit element could be a resistor, could be a capacitor, could be an inductor, could be whatever you want over there. Think of 2 terminals, could be a diode, right. Now, assign input and output quantities. So, for example, you could assign the input quantity. Input means I have applied and output means I measure and observe, fine. So, one, you are putting a voltage, the voltage is the input quantity, and somehow you have measured the current is the output quantity, fine. You could do the reverse, you could apply the current and measure the voltage, whatever it is, right. Either you apply the voltage, measure the current, or you apply the current, measure the voltage, all right. So, whatever you have applied, that is the input quantity, whatever you are measuring, that is the output quantity. Okay. So, let us say you have applied V and you are measuring I. Now, I am going to do 2 experiments. First, I am going to apply V1 and I measure the output quantity I1. And next, I am going to apply V2 and I measure the output quantity as I2. Fine, keep these results. And now, we are going to do a third experiment and apply V1 plus V2 and measure the response. Okay. So, in a linear system, the response has to be equal to I1 plus I2. That is the definition of a linear system. All right. This is how we define a linear system. A linear system is defined in this manner, a system where if I apply V1 I get I1, I apply V2 I get I2, and I apply V1 plus V2 I should get I1 plus I2. Fine, this is the definition of a linear system. So, a linearity has 2 sentences in its definition, 2 different things. One is superposition, which we have described just now, and the second is homogeneity. So, homogeneity can be thought of as an outcome of superposition. Instead of applying V1 and V2 and getting I1 and I2, you could have applied V and V. Okay. In experiment 1 I apply V, I get I. In experiment 2 I apply V again, I should get I, and then next I will apply 2V, should give me 2I, 3V should give me 3I, and so on, right. This is called homogeneity. This is the second principle, homogeneity. This is an outcome, you could think of it as an outcome of superposition, right. Just that irrational scaling factors, how will you generate an irrational scaling factor? So, alpha times V should give me alpha times I, where alpha is some constant, right. This is the second part, this is homogeneity. Okay. So, whenever we talk about linearity, we are actually talking about 2 different things. Most important is superposition. I do 2 experiments, V1 to input 1 gives me output 1, input 2 gives me output 2, then does input 1 plus input 2 give me output 1 plus output 2. If it does, then the system is guaranteed to be linear, okay, and homogeneity is going to follow. Fine. Shake head means no, like this is yes. Okay. Okay, good. That is the definition of a linear system. Now, is your resistor linear? Why? Why is it linear? Because if I apply V 1, I get I 1. I 1 is V 1 by R. If I apply V 2, I get I 2 is V 2 by R, and if I apply V 1 plus V 2, then I happen to get V 1 plus V 2 by R, which happens to be equal to V 1 by R plus V 2 by R, and that proves that a resistor is linear. Fine. What about a capacitor? No. Why not? I apply V 1, what is the current? C times d V 1 by dt. I apply V 2, what is the current? C times d V 2 by dt. I apply V 1 plus V 2, what is the current? C times d of V 1 plus V 2 by dt, which happens to be equal to C d V 1 by dt plus C d V 2 by dt, and therefore, this is linear. Okay, it is a linear operation. So, the capacitor is linear, it has nothing to do with a straight line. Okay. That is why I said do not confuse linearity with a straight line. Y equal to m x plus c is not a linear system. Think about it. X is the input, y is the output. Okay. X is the, so I have a system which performs the following operation: y is equal to m x plus c. I apply x and I obtain y. Okay. If I apply x 1, what do I get? M x 1 plus c. If I apply x 2, what do I get? M x 2 plus c, and if I apply x 1 plus x 2, I get m x 1 plus m x 2 plus c, which is not equal to m x 1 plus c plus m x 2 plus c. So, unfortunately, if c is not equal to 0, right. Unfortunately, if c is not equal to 0, then y equal to m x plus c does not describe a linear system. So, yeah, they are related, but linearity is not about a straight line. Okay. Drill this into your head. This is going to come in many different courses, the same thing is going to be repeated, right, in control theory, in signals and systems. Right away, signals and systems, they are going to talk about linearity again and again and again. In EE, we are going to talk about linearity many times, and every time this definition is going to be given, and every time some of you are going to say no, this can't be right. Right? How can a capacitor be a linear system? But a capacitor is a linear system, and y equal to m x plus c is not a linear system. Okay. So, keep this in mind, because this is going to come repeatedly. So, I need you to understand this. All right. What about an inductor? I can describe the inductor like this, right? If my input is I and my output is V, right? If my input is I, output is V, then V 1 is equal to L d y 1 d I 1 by d t, V 2 is equal to L d I 2 by d t, and therefore, V 1 plus V 2 is equal to L times d I 1 plus d t plus L times d I 2 by d t, and therefore, this is a linear operator, linear system, linear circuit element. Fine. As soon as you throw some initial conditions at this, that is, if you try to write the equation as an integral equation, if your input quantity is the opposite, right. For example, in the capacitor, if your input quantity is V and output quantity, sorry, input quantity is I and output quantity is V, then you will write it as V is equal to integral I by C dt, right. And to do the once you do the integral, you will be left over with a constant, right, initial condition, what happened at time t equal to 0. So, when you throw in these initial conditions, unfortunately, this linearity is not going to be preserved, it is going to become like that y equal to m x plus c. Okay. So, if the initial condition is 0, if initially you have 0, then also it is a linear system. So, we do not have a problem, just say initialize, discharge all the capacitors, right, have the initial current through all the inductors as 0, it is a perfectly linear system. Fine. Any questions so far? Okay. What about a diode? Let us say in the diode the current I is, what is it, some constant times exponential of V by V t minus 1, okay, in a diode. This is the kind of expression you get. Is this going to be linear? Is this linear? Yes, no? Louder. No. There is no way it is going to satisfy linearity. Okay? It is horrible, the equation looks horrible, it can't possibly be linear. All right. So, this is called non-linear. Great. So, R, L, C, M, these are all linear and passive. R, L, C and M, these are all linear and passive. Fine. Diode non-linear, voltage source, current source active. Fine. Is there any question of linearity for a voltage and current source? Mathematically there is no input output, there is no input, right. So, we do not really ask about linearity of a voltage source, it is constant. Okay. So, quickly we will cover one more concept, and that is time invariance. Time invariance talks about whether the experiment you did depends on the time or not. Does it matter if you do the experiment today or tomorrow, will you get the same answer? usually you should, right. But if you have to look at the watch and decide on the output of the experiment, then it is not time invariant, it is time varying. So, most of our experiments are going to be time invariant, whether you do the experiment today or tomorrow, 1 second later, 1 second earlier, 1 millisecond later, 1 millisecond earlier, it does not matter. Okay? Such systems are time invariant systems. Fine. Can you give me an example of a time varying system? Some of you have done digital electronics, right? Some of you have done digital electronics. Yeah, I expect an answer from those guys at least. Give me an example. Any sequential circuit which needs to look at the clock to determine the output, they are time varying circuits, time varying systems. A circuit which does not have to look at the clock is a time invariant circuit. Fine. Is this okay with all? Great. Now, what about our resistor, capacitor, inductor? Are they time varying or time invariant? They are all time invariant circuit components, right. They you do not have to check the time on a clock to tell the outcome of your experiment, right. So, whether you do the experiment now, later, you will always get the same answer. So, all my circuit components are LCM, these are all linear and time invariant. In circuit theory, we are only going to deal with these components. This is a first year undergraduate course, right. We do not want to complicate matters. So, all the circuit components in this course are going to be linear components and time invariant components, right. We are not going to invoke memory, we are not going to talk about a clock, we are not going to talk about hysteresis, right. These all create time varyings, these are all time varying objects, right. Memory, right, RAM, ROM, flash memory, whenever you want to look up something from history, right, that is all time varying. Fine. Our circuits are going to be time invariant. In this course, everything is going to be linear and time invariant. So, we are not going to talk about diodes, we are not going to do transistors, we are only going to do RLCM and a few more. What are the few more? We are also going to do dependent and independent voltage sources. The symbols are like this, they look like a diamond. Okay. So, these are dependent voltage source and dependent current source. So, the voltage across this is going to be some alpha times V1, where V1 is a voltage in some other part of the circuit, or the current through this is some alpha times V1, where V1 is the voltage somewhere else, or it could be some alpha times I2, where I2 is the current through some other component. Okay. So, these are called controlled dependent voltage and current sources. So, you could have a voltage controlled voltage source, where the voltage source value is alpha times V1. You could have a voltage controlled current source, where the current value is some resistance times V or some conductance times V1. You could have a current controlled voltage source and you could have a voltage controlled current source. So, all these 4 possibilities are there. We call them CCCS, V C V S, V C C S and C C V S. Fine, all 4 possibilities are there: current control, voltage control, current source, voltage source. Fine. Any questions? So, this covers all the different components that we are going to deal with in this course. Next, 2 primary fundamental concepts. One is Kirchhoff's current law and the second is Kirchhoff's voltage law. What does Kirchhoff's current law say? It says that if I have a region in space, then the total current going out of this region in space is equal to 0. This is Kirchhoff's current law at all times, at all instants of time. This is true. At each and every instant of time, Kirchhoff's current law is true anywhere in the universe. Okay. So, Kirchhoff came up with these 2 laws and these are really laws. There is no way to break them. Okay. You cannot break them in any place in this universe at any time in past, present or future. You cannot at any instant of time you cannot violate Kirchhoff's current law or Kirchhoff's voltage law. Who was Kirchhoff? Scientist. Okay. He came up with these 2 laws while he was an undergraduate student like you. Okay. Like all of you. Kirchhoff was an undergraduate student, he came up with these 2 laws as part of his undergraduate dissertation, whatever we call it BTech project over here. So, as part of his BTech project, he came up with these 2 laws and the laws are so fundamental that you cannot violate them ever, anywhere. Okay. So, what is KVL? In any loop, the sum of all the potential drops is equal to 0 and you can draw this loop whichever way you like. Fine. So, that is KCL and the other one is KVL, right. Why does this work? Why is KVL true? Potential energy, okay, is conserved, and why is KCL true? Because charge is conserved. So, KVL comes from law of conservation of energy and KCL comes from charge. All right. So, with this let us close for today. Thank you.